Propositional logic. Logic is one of the factors that make up propositional logic. Logic is the basis of all mathematical reasoning and of all automated reasoning. It has practical applications to the design of computing machines, to the specifications of systems, to artificial intelligence, to computer programming, to programming languages, and to other areas of computer science as well as to many other fields of study. The rules of logic specify the meaning of mathematical statements. They also give the precise meaning to these statements. These rules are used to distinguish between valid and invalid mathematical arguments. Besides the importance of logic in understanding mathematical reasoning, logic has numerous applications to computer science. These rules are used in the design of computer circuits, the construction of computer programs, the verification of the correctness of programs, and in many other ways. Furthermore, software systems have been developed for constructing some but not all types of proofs automatically. Another factor that makes up propositional logic is a proposition. A proposition is a declarative sentence, that is, a sentence that declares a fact, that is either true or false but not both. Consider these examples. Propositions 1 and 3 are true, whereas 2 and 4 are false. And these examples, sentences 1 and 2 are not propositions because they are not declarative sentences. Sentences 3 and 4 are not propositions because they are neither true nor false. Note that each of sentences 3 and 4 can be turned into a proposition if we assign values to the variables. We use letters to denote propositional variables, or statement variables, that is, variables that represent propositions, just as letters are used to denote numerical variables. The conventional letters used for propositional variables are P, Q, R, S. The truth value of a proposition is true, denoted by T if it is a true proposition, and the truth value of a proposition is false, denoted by F if it is a false proposition. The area of logic that deals with propositions is called the propositional calculus, or propositional logic. It was first developed systematically by the Greek philosopher Aristotle more than 2,300 years ago. Many mathematical statements are constructed by combining one or more propositions. New propositions, called compound propositions, are formed from existing propositions using logical operators. We now turn our attention to methods for producing new propositions from those that already exist. Let P be a proposition. The negation of P, denoted by dash P, is the statement, it is not the case that P. The proposition dash P is read, not P. And here's the truth table for the negation of the proposition. Another method is the conjunction. Let P and Q be propositions. The conjunction of P and Q is the proposition P and Q. The conjunction P and Q is true when both P and Q are true, and is false otherwise. And here is the truth table for the conjunction of two propositions. Another method is the disjunction. Let P and Q be propositions. The disjunction of P and Q, denoted by, is the proposition P or Q. The disjunction is false when both P and Q are false and is true otherwise. This is the truth table for the disjunction of two propositions. Here's another method. Let P and Q be propositions. The exclusive OR of P and Q is the proposition that is true when exactly one P and Q is true and is false otherwise. And Here's the truth table for the exclusive OR of two propositions. Now, let's tackle conditional statements. The definition: let P and Q be propositions. The conditional statement P implies Q is the proposition if P then Q. The conditional statement P implies Q is false when P is true and Q is false, and true otherwise. In the conditional statement P implies Q, P is called the hypothesis or antecedent or premise, and Q is called the conclusion or consequence. And this is the truth table for conditional statement P implies Q. Because conditional statements play such an essential role in mathematical reasoning, a variety of terminology is used to express P implies Q. You will encounter most, if not all, of the following ways to express this conditional statement. If P, then Q. If P, Q. P is sufficient for Q. Q if P. Q when P. A necessary condition for P is Q. Q unless not P. P implies Q. P only if Q. A sufficient condition for Q is P. Q whenever P. Q is necessary for P. Q follows from P. Now let's get to converse, contrapositive, and inverse of a proposition. We can form some new conditional statements starting with the conditional statement P implies Q. In particular, there are three related conditional statements that occur so often that they have special names. The proposition Q implies P is called the converse of P implies Q. The contrapositive P implies Q is the proposition not Q implies not P. The proposition not P implies not Q is called the inverse of P implies Q. We will see that of these three conditional statements formed from P implies Q, only the contrapositive always has the same truth value as P implies Q. When two compound propositions always have the same truth value, we call them equivalent, so that a conditional statement and its contrapositive are equivalent. The converse and the inverse of a conditional statement are also equivalent. I now introduce another way to combine propositions that expresses that two propositions have the same truth value, biconditionals. Let P and Q be propositions. The biconditional statement of PQ is the proposition P if and only if Q. The biconditional statement of PQ is true when P and Q have the same truth values and is false otherwise. Biconditional statements are also called bi-implications. Here's the truth table for the biconditional statement P if and only if Q. Here's a few common ways to express P if and only if Q. P is necessary and sufficient for Q. If P, then Q, and conversely. P, IFF, Q. Note that P if and only if Q has exactly the same truth value as the conjunction of P implies Q and Q implies P. Here's a table for the precedence of logical operators. The negation or the not operator is always executed first. It has the highest precedence. The conjunction operator comes after it, then the operator disjunction comes after the conjunction operator. Then after it is the conditional operator,
and then lastly, the biconditional operator.
Logic and bit operations. Computers represent information using bits. A bit is a symbol with two possible values, namely 0 and 1. This meaning of the word bit comes from binary digit, because zeros and ones are the digits used in binary representations of numbers. A bit can be used to represent a truth value because there are two truth values, namely true and false. As is customarily done, we will use 1 bit to represent true and 0 bit to represent false. That is, 1 represents t and 0 represents f. A variable is called a Boolean variable if it is either true or false. Consequently, a Boolean variable can be represented using a bit. Computer bit operations correspond to the logical connectives by replacing true by 1 and false by 0 in the truth tables for the operators AND, OR, and XOR. This table is obtained with the corresponding operations. And the bit string is a sequence of 0 or more bits. The length of this string is the number of bits in the string.